Let's go through an example of applying the Clausius inequality. So it may be perverse to call this an inequality, after all it has an equal sign in it, but if you remember, sigma has to be greater than or equal to 0, so that's where the inequality part is coming in. You can also call this the Clausius relation. Regardless, we're going to apply this complicated looking thing to a system and see that actually in most cases it's pretty easy to use. Now when you see an integral over a boundary and different times, you might worry, especially if you've had electricity and magnetism, this is going to be like a Stokes theorem thing that you're going to have to do. No, in this course you basically just have to do some accounting. It's not so bad. So let me show you. This is our system, and I'm going to introduce three thermal reservoirs that at different points will come into contact with when we execute a cycle. So let's execute a cycle. In the first process, we'll bring the 400 Kelvin reservoir into contact with the system. We'll donate 12 kilojoules of energy. Remember, the arrows tell you the direction the energy is moving, and this is heat energy. Simultaneously, we'll get the system to do 6 kilojoules of work on its environment. That arrow also indicates the direction of energy transfer. We'll remove the reservoir just so that we know it's not in constant thermal contact for the other two processes. Okay, so we did that. For the second process, we're going to have 4 kilojoules of work done on the system from the environment, and we're going to be in contact with the 300 Kelvin reservoir, transferring 11 kilojoules of energy out to that reservoir from the system. Okay, remove that reservoir. Final process, we'll attach the 350 Kelvin reservoir, and we'll just donate 1 kilojoule of heat energy from that to our system. So we'll remove the final reservoir. Now we have all of the energy transfers through both heat and work associated with this entire cycle. And if you want to convince yourself it's a cycle, you can go through and just count up all of the energy in and all of the energy out. Should be the same. So how do we apply the Clausius inequality? Okay, I'm going to label the process involving the reservoir at 400 K as process 1. So process 1 has a temperature of 400 Kelvin. The heat transfer associated with that is 12 kilojoules, and we know that it must be 12 kilojoules into the system given the direction of the arrows. So if you remember from the fact that delta E total equals Q minus W, that tells us that we're transferring heat into the system, so Q must be positive. I'm going to label this heat transfer delta Q1 equals positive 12 kilojoules. Now that is slightly sloppy notation on my part, because really delta ought to be a differential. It's actually an inexact differential. If you want those gory details, read through your textbook. But think about what we've done for a minute. We've actually discretized this integral because we have three discrete heat transfers and temperatures. We're just going to take the ratios. If we can do that, then actually the integral just becomes the sum of those three terms. If we're turning this into a sum, then I don't feel bad labeling each discrete heat transfer delta Q. That's all I'm doing. So now if we take the ratio of delta Q over T for process 1, it just becomes plus 12 kilojoules over 400 Kelvin. Okay, so that's our ratio of delta Q over T for process 1. We're going to do exactly the same procedure for processes 2 and 3. Process 2 is the bottom one that involves the reservoir at 300 K. Now that heat transfer has to be negative, right? It's taking heat energy away from the system. So the heat transfer is minus 11 kilojoules. That ratio, delta Q over T for process 2, becomes minus 11 kilojoules over 300 Kelvin. Process 3, same story, it's 350 Kelvin. Heat transfer was plus 1 kilojoules. Delta Q over T for process 3 is plus 1 kilojoule over 350 Kelvin. I'm going to substitute in those values where I have the reservoirs on the left, just so that we remember their values when we try to add them together. So, process 1, process 2, and process 3 all over there on the left where the reservoirs used to be. Now we can erase all this stuff. So like I said, what we've managed to do is basically to discretize this integral just because we only have three individual heat transfers, and that's all that's happening over the entire cycle. So that tells us that this integral of delta Q over T at the boundary over all times is just the sum of the three values of delta Q over T that we computed. So we put in those values. Using the appropriate sign, you need to make sure to retain the correct sign. In this case, process 2 is the only one that would have been a problem since it's negative. And you add all of that together, and you get that it's minus 0.0038 kilojoules per Kelvin. Now I'm actually going to convert back to joules just so that we have a slightly bigger number. And if we do that, we get that the integral of delta Q over T at all the boundaries over all times is minus 3.8 joules per Kelvin. There's one last step, which is to relate this to sigma cycle. You can imagine that we were being asked just to compute the added entropy to this system. That is sigma cycle. So if you look up in the Clausius inequality, the integral we just did is actually negative sigma cycle. So that means that sigma cycle must be positive 3.8 joules per Kelvin. Okay, so remember, that represents the added entropy to our system, the added entropy as a result of executing this cycle, and it's positive. So the implication of that is that this must be an irreversible process. If you get that it's zero, that tells you it's a reversible process. If you get that it's negative, there's two possibilities. Either you found an impossible process, or you screwed up the math somewhere. You might want to double check your work. Don't run to the patent office when you find your first negative number. Odds are something went wrong.